finding zeros is really like if we go back and we think about our earlier chapters. Do you remember in chapter 2 we kind of introduced the parabola and we did all the graphs of parabolas, like what if it's in intercept form, what if it's in standard form, what if it's in vertex form, and it's like all the graph stuff. Okay. And then in chapter 3 we moved on, we kept working with quadratics, but we focused on solving quadratics. So the very first day in chapter 3 we solved by graphing, where we just found their x-intercepts. But we said this is not really a great method for solving because it doesn't always come out nicely, right? So then we talked about solve by taking square roots, solve by factoring, solve by completing the square, which eventually evolved into solve by quadratic formula. So we had all those methods to solve a quadratic. Well, factoring is what we reviewed in the last section, and that was really how we could solve a polynomial. So if solving a quadratic meant we were finding x-intercepts, solving a polynomial is going to be the same thing. So this phrase, finding zeros, we also sometimes say solve the polynomial. Equation. Those two things kind of mean the same thing, and they both essentially mean you're finding x-intercepts on the graph. Now, we also had this discussion back in chapter 2 because of the shape of the quadratic, that it was a parabola, it was U-shaped. There were some times when the parabola didn't cross the x-axis. So remember that if we're finding zeros or we're solving the equations, that we're finding the x-intercepts only for the real zeros. The imaginary zeros are going to be what we call solutions. And they do something to our graph, and that's the thing we don't really know for certain, like how to put that in our graph, what that does. But they're affecting our graph in some way, but we don't see them, we don't have to plot them, worry about putting them on the real coordinate plane, okay? Now, also, I just want to say really quickly that, like, to avoid any kind of confusion, which I think I generally don't say this enough, there are lots of synonyms that I can use for the word zeros. So when I talk about finding zeros, sometimes you also hear that as the roots of a polynomial or the roots of an equation. So if you're asked to find the root, it means basically solve the equation, find the zero. Also, I can use the word solution. Okay, so if I'm saying find the solutions, what are the solutions, how many solutions, that's interchangeable with the word zero, interchangeable with the word root. And x-intercepts is interchangeable, but remember those would only be the real solutions. All three of these words would really imply that they are real or imaginary. So then you have all the solutions. Okay. So we're going to keep on with this whole okay, factor the polynomial. We're using our graphic organizer on the back or on the front of the green sheet. Do we have sum or difference of cubes, difference of squares, factor by grouping, trinomial, and then we're going to solve the polynomial. So we're going to find the x-intercepts. Well, we're going to start putting those things on a graph. So we're going to go back to graphing, which we did in section 4.1. But before we do that, I need to have a brief conversation about multiplicity. Okay, I mentioned this real quickly early on in the chapter, but not enough to make it stick. So here's where we kind of say a few things about multiplicity that we all agree to. Multiplicity means the number of times a zero repeats. And this can happen, you can have a repeated zero. Think about if you factored a polynomial and your two factors were exactly alike. Let's say you factored it and it was x plus 3 times x plus 3. Then when you solved both of the factors, you would only get one answer, right? X equals -3. but because you had two factors, you really had two solutions. We saw that with the parabola. That was when our discriminant was equal to 0. That if we would have factored it, they would have had the same two factors. So we say that when you have even multiplicity, so this would be like if your 0 showed up twice, or 4 times, or 6 times, or 8 times. If you have even multiplicity, the graph turns. Or you might think about that, I often describe it like bouncing. I'm going to say on the axis, on the x-axis, at that 0. So the graph turns at the x-axis. You can look at the graph and think like maybe like it's bouncing off of the axis, so instead of crossing through the axis. That implies even multiplicity. So if you look at the picture that I provided, you know, like where are your zeros? They are the x-intercepts, right? So it looks like I have 3 x-intercepts. So I've got an x-intercept at -2, an x-intercept at 0, and an x-intercept at 1. -2, 0, 0, 0, and 1, 0. Inspect those 3 x-intercepts. Do you see anywhere you're turning on the axis? Turn on the axis at x equals 0, right? You see that like your graph is coming up. It's in the negatives and it touches the 0, so then your y value is 0. But instead of crossing over into the positive, it just turns right back around. Okay. So that means that 0, 0 has an even multiplicity because we can see that on the graph, how it comes up, touches, and turns around. So now you're going to have to be thinking about that if you have a 0 that repeats with even multiplicity. You will show on your graph that it comes up or goes down to that 0 and turns right there. Now, one thing I want to show you is the image of that bounce changes as the multiplicity increases. So I'm going to pull over here. I'm going to do Desmos real fast. This is on projector mode. Okay. Actually, I don't even need the other ones. They probably are. We don't need the number. No, numbers. We don't need the grid at all. How about that? Okay. So I'm going to graph y equals x squared. Okay. That's essentially x times x. So it has the same two factors, x and x. It has 1, 0 at 0. And it turns at the axis, right, at 0, 0. Well, what if instead of repeating 2 times, what if that repeated 4 times? Okay, that's this like blue graph. And what if it repeated 6 times? That's the green graph. Can you kind of see what happens to your bounce when you increase the number of multiplicities, like by even numbers? So the red one was when it was just a multiplicity of 2. And then the blue one was a multiplicity of 4. And the green one is a multiplicity of 6. As your multiplicity increases, it becomes less like round and more flat. Okay. It might even look like it's like touching the axis right there, like it's horizontal, but we know it's not. It's only touching the x-axis at 0, 0. It's just getting really, really close to the x-axis down there. So you could imagine, like, if I did like an x to the 10th, that it would come out even wider, right? It would be rounder. It'd be less U-shaped, okay, that we would think about it. So I'll just put in an x to the 10. See how U-like that is? Okay, so I'll take away the other ones. Compared to a multiplicity of 2, there's a multiplicity of 10.
So the line isn't, the intercept is at 0, 0.
Yeah.
And the line is not actually touching the line.
Yeah, it's really hard. What do I need to? It's hard for me to do on here. If I had like my like a phone, it's easier for me to pinch it. Let me see if what do I want? Closer or less? Let me see what happens if I change this. I don't know which way I want to do it. No, that makes it worse. So let's do 0.001. Oh, that's the y. That's not what I meant to do. I came unprepared for this. Let's try this. -1 and 1. It doesn't really help. It's hard to, if I could zoom in, and we could do this during work time, like we could grab a phone and do it. But like, it's just really, really close to 0. Like I could put my cursor on this line and it's giving me a point. But do you see like it's at like 0.0002 or whatever? So, and at some point Desmos calls it 0, but it's not really at 0. I'm just not zoomed in close enough. The only place it hits is at 0, 0. Okay. Okay, so that's even multiplicity. And then odd multiplicities, because you could have a 0 repeat an odd number of times. Okay. Here's what happens for odd multiplicities. The graph crosses the axis at the 0. So if you ever notice that, like on a graph, the graph is actually crossing the x-axis, that would mean it would have to have some odd multiplicity. The most common multiplicity is really not, like, it's multiplicity of 1, right? Where it doesn't really repeat, it's just a 1, 0. But we would consider that to have odd multiplicity so that the graph is actually crossing the axis. So when I look at the other two zeros, notice at x equals -2, I cross from positive to negative. And at x equals 1, I cross from negative to positive. So I'm actually crossing the axis. So for both of these, I would assume there is some odd multiplicity. Now, going back to our conversation about like how even is going to distort like our u, do you notice there's a difference between those two zeros, like how it crosses the axis? At x equals -2, you have that weird thing, the bend. I call it a bend in my graph. It's not turning, it's not changing direction. If I follow it with my finger, it's still decreasing. It just like takes a little jaunt to the side. Okay, that's because I would assume that 0, x equals -2, I would assume that has a multiplicity more than 1. It's odd, but it's more than 1. So I'm thinking like maybe x cubed. And I'll go back to this slide right here, and I'll get rid of all my evens. Okay, so here's x to the first, which is a line, right? Crosses the axis. Here's x cubed. You see that bend? And then if I do x to the 5th, it gets flatter in the middle. So like if we did x to the 11th, it looks really, really flat. And this is, again, that whole thing. Like, where it looks like it's just on the axis, it's really not. It's, like, so close, but it's really not on the axis except for at 0, 0. Okay? So if I go back to this, I'm gonna guess like for my zeros, like I had listed them over here, I would say something like x equals -2, probably with a multiplicity of 3, because it doesn't look like super flat, right? And then I would say x equals 0 with a multiplicity of 2, probably, because it looks like a regular nice U shape, right? It's turning, so it's got to have even multiplicity, probably 2. And then this one just crosses straight through, no weird bends or anything. So I would say my other 0 would be x equal 1. I wouldn't even say with multiplicity 1, right? If I don't give it a different multiplicity, then I assume it's multiplicity 1. So then think about this just in terms of like bringing it all together. You have 3 zeros of -2, 2 zeros of 0, and then 1 0 of 1 for a total of 6 total zeros. Would that make sense with your graph that your degree be 6? And behaviors? Going up? Both sides? Would that be a degree 6? Yeah. Whereas if you looked at this, and we didn't have this conversation about multiplicity, and you said there's 3 x-intercepts, so there's 3 zeros, you might assume that the degree be 3, but that would mean I'd have to have opposite end behaviors. So we know something's up, right? And there has to be a multiplicity there. Okay, so that's like stuff for you to like chew on, think about as we do our different graphs.
Sorry, I understand that x equals -2 and 0 and 1. Why did you put the 3 and the 2 and the 1 together? Why did they have that?
With multiplicity of 3?
Yeah.
That was like, you see it has the weird bend?
Mm-hmm.
It's probably not multiplicity 1. So I'm guessing it's multiplicity 3.
Oh, okay.
It's odd because it's crossing, but it's got that bend. And what I just showed on Desmos was the bend gets like flatter and flatter the more repeats it is. It really isn't that flat. So I'm guessing it's 3.
Okay.
And then on this one it was 2. We knew it had to be even because it was bouncing. But it doesn't look like super flat. It's just like a nice little U shape. So I'm guessing it's multiplicity 2. But that's all I guess. I don't know what the function is. So I don't know for sure it's degree 6, but that would be my assumption.
So would it be like counted wrong if it was asking multiplicity for like that first one for -2? If we said like 5 instead
No,
of 3?
I wouldn't count it wrong if you didn't have a function.
Okay.
Yeah, you could guess anything. Mm-hmm.
And then for the last one, x equals 1, so it doesn't have a multiplicity, it's just straight.
Yeah, there's nothing weird happening at that cross. It's just crossing the axis. So I would assume if there's no weird bend to it, it's probably just a 0 that appears one time. Because that's like if you think about your quadratics, that's how a quadratic crossed, right? Just like nice clean and through, nothing weird. All right, so that's just like I was saying, stuff for you to think about with the multiplicity. We're going to like have to consider multiplicity when we make our graphs today, but there's some like big concepts there that like you don't have to always be super concerned with, but it's just good for you to know. We're going to graph f of x equals x to the 4th minus 4x cubed plus 4x squared. And what I'm going to change about today, because we know more about polynomials now, rather than having to make that list, that table, x, y, and fill in all the points, let me solve the polynomial, find the zeros, which will be x-intercepts, plot them, maybe look at my y-intercept real fast, because that's easy, that's my constant, plot the y-intercept, so I'll have like a sampling of points, and then check my end behavior and draw my graph. I don't have to do the whole like substitute in different x's. So what would you do first to solve this polynomial by factoring? Take out the x squared. Take out a greatest common factor. So we've got x squared minus 4x plus 4. After you take out a GCF, always check what's left over. We're left with a 3-term polynomial. That's a trinomial. So I would try to factor it by guess and check. Sometimes it will factor, sometimes it won't. Do you have factors of 4 that add to make negative 4? Yeah, minus 2 and minus 2, right? So x squared minus 4x plus 4 factors out to be x minus 2, x minus 2. And you can leave it like this. You could also write this as like x squared times x minus 2 quantity squared, right? What I like about that is when I write it with the exponent, I know it repeats, right? This is multiplicity. Its multiplicity is equal to its exponent. Even this x squared has multiplicity. X squared really means x times x. So you had like 2 factors of x times x minus 2 times x minus 2, that make this quartic polynomial. Okay. So either way, it's factored, right? Okay. All right, so step 2, set your factors equal to 0. So if you want to use like this form, you would say x squared equals 0, x minus 2 equals 0, and x minus 2 equals 0. Or you could use this one where you have them repeating and you'd only write them once. Well, if I'm solving x squared equals 0, I could certainly square root both sides. And I don't even think you really have to do math. Don't you know the answer is going to be 0 there? The only thing you have to be careful of is remember, how many x equals 0s did you actually have? 2. So we're going to say x equals 0 with multiplicity of 2. Now, if that was x cubed, I would say x cubed equal to 0. X would still be 0, but it would be with multiplicity of 3. Right? So the multiplicity is going to equal the exponent on the x. Okay, because that's x times x times x. There's really 3 factors. On the other two, of course, I would set it equal to 0, and aren't I going to get the same answer for both of those? Like they're both going to be x equals 2. So I'm really only going to solve one of them and say this is x equals 2 with multiplicity of 2. And again, I could have just set these equal to 0 and said that their multiplicity matched their exponent. For the 2? Because x equals 2 would solve in this first factor, and then I would get the same answer, x equals 2 in this one. So rather than writing 2 and 2, I'll say it's 2 with a multiplicity of 2. It shows up twice. I could have solved this one, and I would get the same answer, so that's a multiplicity of 2. Okay. Okay, so both of my zeros have even multiplicity, right? What happens at even multiplicity? It bounces. Okay, so we'll have to remember that when we make our graph. See, I got an x-intercept at 0, and I got an x-intercept at 2. I'm going to go back up to my original polynomial real fast, way back up at the top. What's my y-intercept?
0.
Oh, also 0, right? It's the constant. So I've already plotted that point on this one, haven't I? Because I put my x-intercept at 0. So that one's done. I've got that. And then just like we did in our warm-up, what's our end behavior? As x approaches positive infinity, what's y doing? It's going to positive infinity because it has a positive 1 in front. And on the left side, as x approaches negative infinity, what's your y doing? Also going to positive infinity because even degree means it's the same. Okay. So when I take that end behavior back to this graph down at the bottom, I only have 2 points. But I know on the left side, I have to be rising. And on the right side, I have to be rising. Right? We just said that y's were going to positive infinities. And I know that I have even multiplicity, so when I get down to this 0, I must bounce. So my brain is kind of filling in what could happen. I'm going to do it in dotted lines first. Bounce, come up, must come down, but this is even multiplicity, so I bounce. Could it look like a W? Would that make sense? It would have the right end behaviors. It goes through the correct y-intercept at 0. It has the zeros of 0 and 2 with even multiplicity shown by bouncing. Yeah, I think it's good. So I'm going to fill it in. If you don't find any other points, your graph might look slightly different than mine. Like, how do you know how high to go or how low to go in the middle? The one thing you won't do is draw it right across the x-axis, right? You know you have to bounce up and come back down, okay? If you wanted to, you could pick another point. Like if you wanted to know what was happening in between 0 and 2, I could let x equal 1. I could plug that in. 1 minus 4 is negative 3 plus 4 is 1. So the y value would be 1 and go right 1, up 1. Does that make sense? Yeah. So if you wanted to, if your brain was like, cannot compute, cannot put together a graph, then you would go back and you would find more x's and then get their y's. If you picked like negative 1 over here, you're going to get something that shows that your right side is, or your left side is rising. All right, I think we have time for one more. I'm going to go a little bit faster on the next one. Okay, that's what I expect to see on your homework tonight is like finding the zeros, graphing the zeros, considering your end behaviors and y-intercept. This was actually one from a homework assignment. I think it was like 2 days ago, this f of x. You factored it. So this one has 4 terms. It's going to factor by grouping. It has no greatest common factor. So we're going to say x squared times x minus 8. Take out the minus 4. That leaves me with x minus 8. And x minus 8 matches, so it is factorable. But remember, you're like undistributing the x minus 8, so there's not 2 of them. You only write it one time, x minus 8. And the other factor is x squared minus 4. And then I think we had questions on this one in a class because when you look at x squared minus 4, that factors again, right? It's a difference of perfect squares. So we factored again x minus 8, x plus 2, x minus 4, or sorry, x minus 2. So I'm going kind of quickly through the factoring, but again, that's one on a homework assignment. We've done that one. I think I did that for each class the day we did it. But we would then set all of those factors equal to 0. So we already know what our answers are going to be, right? X equals 8, negative 2, positive 2. Okay, just move that term over when you set it equal to 0. Do any of those have multiplicity? No, each factor appeared only one time. So because I don't have to label any multiplicity on those, what I know is going to happen at each of those x-intercepts, my graph is going to cross the axis, right? Go from positive to negative or vice versa. Okay? Let's see, I'm going to plot those points. So negative 2, positive 2, and 8. What other point would be very easy for me to plot? Doesn't take much work at all. 32, the y-intercept. Okay, y-intercept is equal to my constant, which is 32. Oh gosh, my graph is, I'm going to scale, I'm going to say, here's my 32 way up here. I'm fine with that, it doesn't bother me. Okay, you could scale it if you wanted to, right? What's my end behavior doing? Rise, fall. Okay, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity. So what I know is beyond this negative 2, I must be falling. So I'm going to come up, cross that negative 2, pretend I did. I'm going to go through 0, 32. I'm going to come down. Remember, 2 has a multiplicity that's odd, so it's going to cross the axis right there. And then I'm going to have to make like a quick turn right here. Also multiplicity of 1, so it's going to cross the axis. And isn't my right side supposed to end with rise? So now if I'm solving the polynomial anyway and finding the zeros, I can use those zeros as my points, and I don't need to use the table of values. But if your brain is stuck and you're like, I don't know what this polynomial looks like, what should you do?
Do the table.
Do a table, pick some x's, it doesn't matter what. And it'll get you some more points, like it'll plot a point right here for you, and you'll be able to move on. I was really teaching hard. I lost my scarf.
The brain doesn't work. You're an idiot.